Anyway, let's make a start. So for today, we're going to be having a look at the normal distributions, the next of the probability topics. We last had a look and finished continuous probability. All we have left is normal distribution and sampling and estimation, which we'll look at next week. And then from that point onwards, we have effectively looked at everything for Unit 3-4 at this point. So from that point onwards, Class 2 will essentially be a SAC revision for the upcoming probability SAC. And once everyone's completed that, we will then move on to doing the exam revision itself, which will be quite nice. Basically going through all the past exams and working on those together. But let's not get too ahead of ourselves. Starting with normal distribution. So I brought this picture up a couple of times actually. The normal distribution is a bell curve type shape. It is centered at its mean. 50% of the probability will be to the right of the mean, 50% of the probability will be to the left of the mean. And the way in which the probability is distributed follows that sort of bell curve like shape, where closer to the mean has more net area than further away from the mean. There is an equation that describes exactly this shape. It's not necessary for you to have this memorized. However, it is kind of nice to have and know what the equation is, because it explains a little bit about why each term does what it does. You'll notice a few key symbols that we've seen before, the standard deviation and the mean. And so if you look at the location of the standard deviation terms, those would be in the place where a dilation factor essentially is. Right, you've got this coefficient on your exponential, and the standard deviation plays a role in that. It's part of a dilation factor for it. Same thing if you look in like the x spot, where you have some horizontal translation, that being the mean, and some dilation factor, that being the standard deviation. And if we know anything about dilation factors, it's all about spread, which makes a lot of sense for the standard deviation, right? It's a measure of spread, and so it makes sense that the standard deviation term should change whether you have a nice and tall normal distribution or whether you have a long and flat normal distribution. Larger standard deviations are going to cause it to go flatter because the probability is more spread out. Smaller standard deviations are going to give you this sort of thing, where more of the probability is concentrated right next to the center. Oh, sorry, I completely forgot. For those who are new here, I'll just quickly introduce the setup that we have. So if you have a scroll through, you'll notice obviously everyone's accounts, but one of those accounts is actually my camera. It's currently aimed at the CAS calculator. It'd be a good idea to give that a pin, because we'll be jumping back and forth between the screen share, which you'll see on the top of the Zoom meeting, and the camera itself, whether we do any maybe CAS work or if we do any handwritten work. But yeah, just shout out if you need any help identifying where we're at any given point. For now, we're just talking out of the screen share. But cool, okay, so that's the basics of the normal distribution. Again, you don't need to have this function memorized at all, but it's kind of nice to see how it all plays together. So, how do we normally solve normal distribution questions? Typically, these are CAS questions. There are CAS inbuilt functions that will do the normal distribution for you. The most common of which kind of question is going to be to find a probability between some upper and lower bound. A very typical wording of it is going to be as follows. A normally distributed random variable has a mean of 160 and a standard deviation of 8. What is the probability that x is between 140 and 170? Now, they might not specifically say like x between 140 and 170. They might use the actual key scenario itself, like maybe it's the heights of young women, or the what's another one, IQ scores. And it'll say like, what's the probability of IQ being 100 or higher, so on and so forth. What you'll notice every time is that they give you the mean and the standard deviation. those are pretty much always going to be crucial in calculating probabilities using the normal distribution. When it comes to doing it TeX active, which is what we're looking at right now, the function you're looking for is the normal CDF. Right, kind of similar to how we use the binomial CDF for binomial probabilities in a range. We use the normal CDF for normal probabilities. So if we look at the CAS from the document camera, if you go to menu, 5 for probability, 5 for distributions, you'll see the normal probabilities are up the top. Normal PDF, normal CDF. The one that we want is the normal CDF. You'll see it requires the lower bound, the upper bound, the mean, and the standard deviation. By default, the mean will be given as 0 and the standard deviation will be given as 1. We will, by the end of this lesson, understand why that is the default. But for now, let's plug in the values that we have. So it was between 140 and 170, so the lower bound is 140, upper bound 170. The mean was given as 160, and the standard deviation was given as 8. Plug it all in, 0.888. That is the probability that your result will be somewhere between 140 and 170, so long as you are calculating using the normal distribution. And it'll always tell you it's a normally distributed variable, or more specifically, a normally distributed random variable. Any questions so far? Feel free to hop off mute or even leave a question in the chat. Cool.
So,
oh, yep, question.
is there any way to calculate this not on CAS or?
Yep, so there is. That's where you get into some of the tech-free examples, which we'll start looking at in a moment with confidence intervals. It's where you start essentially approximating the probability. You know, the normal distribution is a very complicated function, and so you're not at all expected to do like an integral, for instance, an integral from 140 to 170 and trying to integrate this thing, although that would work, right? This is within the bounds of continuous probability. It's this whole idea that the area under the curve gives you the probability of that particular range of outcomes occurring. And so yeah, you could technically do an integral on this function itself. However, that's not at all expected. When it comes to tech-free, what you do is you use these approximations where the values that you're given will be some multiple of a number of standard deviations, and based on that, you're essentially trying to figure out what slice of probability you're in, whether you're in maybe the 68% band, the 95% band, or some intermediary slice in between there. But we'll look at that in a bit more detail later. Okay. Cool. Okay. Next up, finding an upper or lower bound given a certain probability. So again, mean and standard deviation are given to you directly. This time the probability is given to you. The net probability is 80%, but you want to find the particular x value, or in this case it's written as k, for which 80% of scores are below. What that looks like mathematically would be this. Right, probability that x is less than k, right, 80% of scores are below k, x less than k, is equal to 80%. The way that we solve this kind of question is with the other function that I didn't mention, the inverse normal. So again, if we have a look at our CAS in the exact same area, option number 3 is the inverse normal. And the syntax of which is you need to know the net area, or the net probability, the mean, and the standard deviation. Those are the things that you need. Now, for those using the TI Nspire, like I am, you have to make sure that the probability you write is always pointing left. And what I mean by that is, in this case, it's already written perfectly. 80% of scores are below k. If it said above k, you need to rewrite that probability in a certain way such that you do have a less than symbol in there. And that will often be done by using a complement probabilities approach. like for instance, if you look back at the screen share, I do detail how you can flip that. Right, like if you're asked to find x greater than a certain thing, you need to now flip that by doing a 1 minus, thus getting your area pointing left. This CAS unfortunately is limited in a way where you do need to have that area pointing left. For those using the Casio, the white CAS, you actually can choose what the tail is going to be. You can choose whether or not you are pointing left or pointing right. You don't have to do this. But okay, we're already pointing left, so we don't have to worry about that. All we do now is just plug in the information that we have. So the net area probability is 80%, so 0.8. The mean was given as 10. The standard deviation was given as 0.8. Hit enter, and we're going to get the particular x value that accommodates that net probability. So what did we find specifically? I will demonstrate by drawing a picture. Just give me a moment to sort that out. Okay. So, what did we actually just find here? Here is our normal distribution, our bell curve. We were told that the mean was 10, which means the center of this bell curve is 10. We wanted to find the value of k such that 80% of the total area is left of that value, less than k. What we just found there was the k value. It was 10.67, which should make a decent amount of sense, 10 being the center. If you're looking for 80% to be left of this value, then k needs to be greater than 10, if you imagine this as like a number line. And the standard deviation of 0.8 means that one standard deviation to the right here would have been 10.08. Hang on, have I got that right? Yeah, 10.08. Nope, I haven't got that right. 10.8. You're adding 0.8 to the value. So one standard deviation will be a little bit further along. If we think about our net probabilities, the approximate probabilities, if 68% is between plus or minus one standard deviation, then it should make a decent amount of sense that if you go all the way to the left, getting 80% seems about right for that. So these are just some things you can do to maybe validate your answer. You don't really need to do this unless you're doing things tech-free. You can pretty much safely rely on your CAS to answer these kinds of questions. Any questions about what we actually accomplished in that? Cool. Alright, tech-free time. So you are going to be required to know these approximate probabilities. There is the 68% rule, which means that between plus or minus one standard deviation, you have 68% of the total area. 95% rule, in which case plus minus 2 standard deviations gives you roughly 95% of the total probability, and plus minus 3 standard deviations, which gives you 99% of the total probability. You will need to have these approximations memorized, because you may get questions like this in your tech-free exam or SAC. So, how do we handle them? Let's have a look. Normally distributed random variable has a mean of 100, standard deviation of 15. What percentage of scores lie above 115? First thing I want to do in a tech-free environment is just draw that normal distribution. The only thing you really care about for now is getting the bell curve right and setting the center of it equal to the mean. Right, so you got 100 as the direct center of that. From there, we're looking for this. Right, what percentage of scores lie above 115? So to be above 115, it's going to be somewhere right of this mean, and we're looking for, at least on this diagram, whatever's right of that 115 here. Now, as for how you get these probabilities, we are looking to find how many standard deviations right or left is this value. So if we're starting at 100 and the standard deviation is 15, then to get to 115, that means you are getting one standard deviation to the right. That's what 115 is representing. And so if you are within one standard deviation to the right, the thing that matters here is the 68% rule. That states that 68% of the total area is going to be between plus or minus one standard deviation. That gives us a starting point. From there, because we know that 50% of the total area is going to be left and right of the mean, we already know that 50% of our total area is accounted for just by saying left of the mean. We know that 68% is within either side of the mean, plus minus one standard deviation, which means half of that, 34%, is going to be just on the right hand side. From there, because 100% is the total area under the curve, you're essentially just adding these ones up and subtracting from 100 to get the net probability that is in the section that you care about, which is above 115, right of 115. That's all it is. In this case I just did two subtractions, but you could just as easily have added those up and then do 1 minus that. That's how you do this in a tech-free way. You start by drawing your normal distribution by setting the mean as the center, in this case 100. You're looking at this to say whether you're above or below a certain number. Then from there, you're looking at how many standard deviations does that number represent, and whether you're going left or right. If it's 115 and you're starting at 100, well, that's going to mean one standard deviation right, which is why we picked our 68% rule as a baseline to start off with. Any questions there? TechActive, we basically already discussed how this works. Only thing is, we didn't really look at what happens if your upper bound or lower bound is boundless, in which case you're just putting an infinity symbol in there. So for this, again, we're doing x is greater than 115. If you were to put in all the relevant stats into the CAS normal CDF like we did before, we're going to get 0.159, which, well, pretty damn close to our approximation. That's pretty much it for just regular normal distribution questions. So we'll start giving those a practice, but before I dive in, is there any concepts that need to be clarified further? Cool. Let's do it then. Let's go. We already kind of did these. I actually kind of ripped this question and used it as the example. So let's go ahead and do question 3. Okay. Heights of young women are normally distributed with a mean of 160, standard deviation of 8. What probability, or what's the probability of being between 152 and 168? Okay.
Sorry.
Yep.
If we are doing a normal probability without a CAS, are we supposed to know the inside fraction or like percentages of like 34? 34. How much are we supposed to know? 34% or 34 point or whatever?
Oh, just the so it's the 68, 95, and 99 rule, and then you divide down from there.
Yeah. Okay.
Yeah, no decimals. This was just a more accurate picture to what it actually is, but these are the things you actually care about. There's no decimals in there. Cool. Okay, so part A, between 152 and 168. So what do? Well, just like I mentioned before, we start by drawing our normal distribution. The mean was 160, so that's going to be the center of our normal distribution. And the thing that we care about is to be between 152 and 168. So 152 would be a little bit left, and 168 would be a little bit right, which means we want to find the probability in here. So how are we going to do it? Well, we need to know what 152 and 168 mean in terms of standard deviations. If our standard deviation is 8, then that means 152 centimeters puts us one standard deviation to the left. That's 160 minus 8. And 168 is even easier to spot. That's going to be one standard deviation to the right. So this is effectively plus minus one standard deviation. This one's a bit of an easier question. We already know off rip, just by being between plus minus one standard deviation, that's just 68%. There's no like area slicing that has to really be done here. It's just 68%. We all cool with how that was done? Cool. Next up, the next question is greater than 168 centimeters. So we can still use the same sort of diagram since the mean and standard deviation haven't changed. Greater than 168 means doing all of this area, everything to the right of our 168. Again, we've already calculated this is just one standard deviation to the right, so the 68% rule is the thing that we're going to care about here. If it's 68% that's between plus minus one standard deviation, then what that means is this slice from the mean to the to one standard deviation is going to be half of that. So half of 68, looking at 34 there. From there, you pretty much always use everything left of the mean as 50%. So maybe we'll just knock off this tick that we have here. That accounts for a total of 50% plus the 34%. And then subtracting from 1 to get the remaining bit here. We've done exactly this before already, which was just with different numbers, different standard deviations, different means. This one's going to come out to be 16%. 16%. All good. Okay. Final question. This one is less than 136. So 136 is going to be significantly further down, and we want to be less than 136. Let's just go ahead and knock some of these off. So again, the question is 136. What is that in terms of standard deviations? What is that? Is that 3 or 2? Let me have a think. So we got a mean of 160. Take 8 is going to be 152. Take 8 again is going to be 144. Take 8 again, 136. So that's going to be 3 standard deviations away. So for this one, that is 3 standard deviations, which means our baseline that we're looking at is going to be the 99% rule, which means 99% of the total area is going to be between plus minus 3 standard deviations. If 99% of the total area is between 3 standard deviations, then that means that the remaining 1% must be equally shared either side of that. So if 1% has to be shared equally either side of it, that leaves 0.5% for the bit that we particularly care about, which is left of 3 standard deviations. 0.5%. Any questions there?
Could you show a way to do it on the CAS?
On the CAS? Yeah, sure. So if we do this in a tech active way, it was less than 136. So all of these are finding probabilities. If you're trying to find normal probabilities, what you're trying to use is the normal CDF. So we go ahead and use a normal CDF. All we need to do is put our boundaries in here. Less than 136 means all values less than 136. What you got to understand here is that because the normal distribution is an approximation, sometimes it's not going to make sense to put a negative infinity there, but you still have to put it there. This is supposed to be approximating heights of young women. No one's going to have a negative height, and yet still, because we are using the normal distribution as an approximation for the probabilities, we have to abide by its rules, which means less than 136 does not cap out at 0, but does actually cap out at negative infinity. Upper bound, that's just going to be 136 since we want to be less than 136. Again, don't round this down to 135. This is not discrete. This is continuous. And because it's continuous, you have essentially infinite decimal places between steps between your outcomes. So the next number is not 135 rounding inwards, it's 135.9999999 recurring. Anyway, and then the mean that was given was 160. The standard deviation that was given was 8. So if we're lucky, we should get 0.5%, which we don't exactly get, but it's pretty close. So 1% is there. Yeah, it's a little bit off, but we are also truncating quite a bit of that 99%. It's 99.72. So realistically, there's only 0.28 that needs to be distributed either side, which now winds up a lot more with what we're seeing, because if it's 0.28 either side, then 0.001 makes more sense. So, we have some trade-offs when we're doing it tech-free, but that is what's expected of you to do in tech-free, so it's not like you're getting it wrong necessarily. All cool with the tech active way of doing that? Cool. Alright, is there anything else? Let's see if we can do one of the inverse normal ones. Percentage, 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 find probability, standardized. Okay, these are a different kind of question. Do we get to do an inverse normal? Not here. That's fine. Okay, so the next set of questions here we haven't actually had a look at yet, which is this idea of finding a standardized value. I haven't explicitly taught how we do it, but the procedure that we've just been going through is more or less what you need to do. What we were doing was looking at our numbers and thinking about them in terms of standard deviations either to the left or to the right. For instance, the last question that we just did had the value of 136, and we knew that was 3 standard deviations to the left. What it means by standardized value is literally replacing that number of 136 with -3, because that would be 3 standard deviations left. That's what it means by a standardized value. There is some sort of equation that you can do that converts your x value into a number in terms of standard deviations, which is usually reserved the variable z. I'm going to have a look at that now. This is what's referred to as the standard normal distribution. It is a conversion formula, or there is a conversion formula that can convert any of your x values to an equivalent z value, where z is just effectively a number of standard deviations. The standard normal distribution works exactly the same as the regular normal distribution, except it's a very specific version of it. It has a mean of 0, so it's always centered at 0, and it has a standard deviation of 1. That's why when you look at your CAS and you use the inverse normal, or even the normal CDF, the mean and standard deviation are by default set as 0 and 1. And yeah, what you'll find is that questions that refer to the standard normal distribution, you'll often write in terms of z rather than x. So how do we actually convert between our z and x? It's with this equation here. And we've kind of done this implicitly already, which is to essentially do a quick calculation of whether you're left or right of the mean. That's the whole x minus mean. And then dividing by the standard deviation will get you to z. We've done this implicitly, but here's an explicit equation for it. So what this means is, so long as you know 3 of any of these given variables, you can solve the 4th variable. It doesn't have to be always going from x to z, you can go from z to x. Furthermore, if you know z and x, and one of the statistics, you can now calculate one of the statistics. Pretty much every time the standard normal distribution comes up, you'll be given additional information about the regular normal distribution. That's what we saw here. Right? Regular normal distribution was mean of 160, standard deviation of 8, and it wants us to standardize the value, or in other words, find the z equivalent of these x values. You have x, you have standard deviation, you have the mean. We want to find z based off of those things. More likely in an exam or SAC scenario is going to be something like this. Because these are quite trivial, you just take, okay, I have the mean, I have the standard deviation, I have the x, I just put those in the mean, standard deviation, and x spot of my equation, and whatever comes out is my answer. Nice and easy. What's more likely is something like this, which directly compares the normal distribution with the standard normal distribution, and you have to find either the x or the z, depending on which one has the variable in it. So let's have a look. X is a normally distributed random variable with a mean of 6 and a variance of 4. Notice that I said variance this time rather than standard deviation. Let z be a random variable with the standard normal distribution. Find b such that this is true. Right, probability of x being greater than 7 is the same as the probability of z being less than b. We have this direct comparison between an x-related probability and a z-related probability. The thing that we know pretty much all the information on is the x thing. Right? We have the mean, we can calculate the standard deviation by just square rooting the variance, and we know its probability of x being greater than 7. Right, we have our x, we have our mean, we have our standard deviation. We have everything we need for this left-hand side bit. What we don't have is the z-related information. Unfortunately, the way this question is worded, you can't necessarily just plug in those numbers and immediately say z equals whatever it ends up being. And the reason why is because these inequalities are pointing in different directions. The left-hand side is a greater than symbol, the right-hand side is a less than symbol. So one of the first things you want to do is make sure that your inequalities are pointing in the same direction. Once they're pointing in the same direction, then yeah, absolutely, you can plug into your z equation. How do we get them pointing in the same direction? Well, we're going to draw up our normal distribution. It has a mean of 6, so it's going to be centered at 6. The probability we have is x greater than 7. 7 is 1 more than 6. And because of the inherent symmetry of the normal distribution, rather than go right 1 and then look right, we can go left 1 instead and look left. These are equivalent areas and thus equivalent probabilities. Useful, because we have now flipped the inequality to now look more like the one that we're comparing it to directly. Now that they're directly comparable, we have our actual x value, we have our standard deviation, which will end up being 2 from square rooting the variance, we have our mean of 6, we have the 3 variables that matter when it comes to solving for z's. Even though it says b, because it's a z probability using the standard normal distribution, we are calculating a z score. So just plug them all in into those spots, and what you'll find is that z comes out to be -0.5. A negative value makes sense because we're looking left of the mean, and the standard deviation being 2 also makes sense because we've only moved 1 to the left. Right? 1 to the left is half of a standard deviation, and so z being minus a half means you've moved half a standard deviation to the left. So in a way, you don't really need this equation if the numbers are easy enough to calculate. But it's obviously going to be nice to have because the numbers are not often going to be nice to calculate. Any questions with how this kind of question goes? Here's another one. In this case, we are given both x and z related information, right? We're given the probability of an x thing, we're given probability of a z thing, we're given the mean. The thing we're not given is the standard deviation. Find the standard deviation. As I mentioned before, this equation is multi-purpose. So long as you have 3 of the 4 variables, you can find the 4th remaining one. Again, one of the things we want to do is make these things more comparable. We have a less than symbol on the left-hand side, and we have a greater than symbol on the right-hand side. Not great. So let's try and do a bit of rewriting. The one that you choose to rewrite is pretty much going to depend on complexity. Like this thing here is more complex to look at than this, so probably better off to try and rewrite this without the 1 minus, so that way things are more easily comparable. There was a similar sort of rationale over here, which is we just had a lot more x-related information, so it was easier to rewrite the x thing than it was for the z thing. But realistically, like, you can rearrange either. Like there is a solution set where you flip this to go greater than. There is a solution where you flip this to be a greater than. But make life easier for yourself and just turn the more complex thing into the less complex thing. So again, we are going to sketch out what this ends up looking like. Since we are focused on flipping this z to go in the right direction, we're going to do our standard normal distribution. So we're going to have the mean of 0, and we're going to draw out what 1 minus probability of z being greater than 1.5 is. 1.5, that's just 1.5 standard deviations to the right, and therefore z being greater than 1.5 means you are looking to the right hand side. Cool. But that's not exactly what we have. We have 1 minus that. Well, using complement probabilities, 1 minus that means you're just looking left instead. Alternatively, another way of now simplifying this is to say, okay, well, that's just saying z less than 1.5. I don't need this 1 minus greater than, I can just do a less than. Now they are directly comparable because the inequalities are pointing in the same direction. We have an x value, we have a z value, we have the mean. Plug in the x, z, and mean in the right spots, and you'll find that only one variable is left in your equation, which you can then solve for. Any questions? Cool. That's all of normal distribution. So let's practice some of the basics of the z equation thing on this standardized value. So we're given mean of 160, standard deviation of 8. What is the standardized value of 160? Without even using the equation, it's just going to be 0. You know, 160 centimeters tall is exactly the same as the mean, and the way it's going to work out is since the mean of the standard deviation, since the mean of the standard normal is 0, that's just going to be 0. But let's just use the equation anyway to show that it comes out to be that way. The equation is as follows: z equals x minus the mean over the standard deviation. Z is equal to 160 minus 160, and at this point, well, we've already got 0, so we don't really care what the standard deviation is, but let's just put it in anyway. Z equals 0. So if it's tech free, you can usually do this intuitively, just by sort of looking and counting how many standard deviations right or left are you. It's where you get weirder numbers like 150 that you can't really do that all too well, because that's not a clean standard deviation to the left. You know, if we're starting at 160 and the standard deviation is 8, that should get you to 152, whereas we want 150. That's where the equation starts to matter, if it's not a multiple of the standard deviation. For the hell of it, let's just do it for that one, and then we'll probably move on to a different question, unless you guys want to see more practice using the z. Z equals x, which is 150, minus the mean of 160 over the standard deviation of 8. 150 minus 160 gets you minus 10 over 8, minus 5 over 4. So less intuitive to be able to just look at that and know what that's going to be. Cool. Do we need to practice any more of those? That's stuff like question 11. They also like to give you these big tables where it's like, hey, here's the mark, the x value, the mean, the standard deviation, and here's the standardized version of that. This, by the way, is what grading to a curve looks like. You get it to a standardized mark across all subjects. It's kind of, I mean, the ATAR works differently. I doubt it would be exactly this equation. But this is more or less how we can compare different subjects to each other. We look at the mean for that subject and the standard deviation for that subject and compare it to the mean and standard deviations of other subjects. And using a z equation or similar, I don't really know exactly what VCAR use, but in that way you can standardize marks across different distributions of grades. Because, you know, like in this hypothetical here, English grades are skewed way higher than math or French. Right? People just tend to do better at English than math or French. And so how do you compare that to math or French? Well, you do some sort of equation like this to standardize it. And that, yeah, that allows you to determine who's the best student overall, just based on who has the higher standardized mark, or I guess the higher average standardized mark in this case, because you're going to get 3 of them. Anyway. Okay, yeah, here's where we do this inverse normal stuff. Cool. Yeah, and you can also do these kinds of questions on the CAS as well, right? Like this one here, you got a mean of 100, you got a standard deviation of 6, and it's asking you to find both the upper and lower bound such that you get 95%. When it's a CAS question, you don't use the plus minus 2 standard deviations approximation. You need to actually use your CAS inverse normal to get the actual proper answers for this. It'll be pretty close to plus minus 2 for your standard deviations. So what's that going to be? 12 either side of 100. As for how you do it, just remember that if you're using TI Nspire, it's always got a point left. So to show what that means, yes, we're given 95% as the boundary, but we need to know what's left over as well. So to be finding the lower bound of this 95%, for instance, we need to know that 0.025 is left of that, because the area that we need to put into our inverse normal needs to be a left pointing area, a left pointing probability. So we go to our CAS inverse normal, 0.025, mean of 100, standard deviation of 6. We're going to get our lower bound of 88-ish, which if you look at the book again, C1, our lower bound is roughly 88 there. To get the upper bound, again you need a leftwards pointing area, but the leftwards pointing area has to point all the way left, all the way down to minus infinity. So you don't just put in the 0.95, you're putting 0.95 plus 0.025. You want everything left of that tick, of that interval. So 0.95 plus 0.025 is going to get us, okay, well, 0.975. From there, I'll just copy the syntax down from here. 0.975, mean and standard deviation haven't changed. 111.76-ish, which again, if you check the textbook, gives you the right answer there. So you got to do a little bit of playing around with the areas that you actually plug into the CAS, which is the same sort of skill that you need for doing the tech-free version anyway. You need to be able to play with what's actually left or what's actually right of a certain tick or interval. Okay, so the first set of questions in this is pretty much just getting you used to Z. It works exactly the same way as when we were finding probability of X being less than something. In fact, it's even easier because all of these are a certain... Actually, this is going to be tech active because they start using non-integer standard deviations. The good thing about Z is that you're just looking at the standard deviations left or right. But because it's starting to use fractional versions of those, you can't rely on these approximations anymore for those particular questions, so these would be assumed tech active. The integer ones are fine, like you can just do those. But okay, here we go. Here's the kinds of questions I was looking for. So suppose Z is the standard normal random variable. Draw a diagram and find the value of C such that Z less than or equal to C is equal to 0.9. Definitely pay attention to the way the inequality is pointing. If it flips, that's going to matter for what we plug into our CAS. And this one we're kind of happy because, again, leftwards pointing stuff is what we need for this CAS. So, still a good idea to draw a diagram anyway, just so we can be sure that our understanding is indeed matching the actual question itself. So, for Z less than equal to C equals 0.9, if we draw out our standard normal distribution, 0.9 is going to be most of this distribution, so the tick that we're looking for should be quite far along. It's the standard normal, so the mean is going to be 0, should we wish to draw it. But the only real thing that mattered was to say, okay, we want it to be less than or equal to some value C, which means we want all of this probability to equal 0.9. Right, everything left of C should equal 0.9 as per the question. Once we have our diagram, or you can just rip it straight into the CAS if you're feeling confident, you then just plug in things into the right spots. So since we're finding an X value, or I guess in this case a Z value, that's when you use the inverse normal. You're given probability information and you want the X or Z. Since it's Z, it's already auto-populated for us, mean of 0, standard deviation of 1. So we're just going to hit enter on that, thus getting 1.28, which is, yeah, still less than 2 standard deviations away, which should make sense. 2 standard deviations plus minus would be 0.95, and since we want to be fully left of C, rather than in between 2 boundaries, makes sense to be slightly or even decently less than 2 standard deviations. Any questions there? Okay, so question 6, question 7, those are the same basically. You just redraw it to say 75% or 97.5%. When you get into questions like 8 and 9, because the inequalities are pointing in a different direction, we now need to flip things around a little bit. So let's do the first one of those, which is question 8. Okay. So again, drawing out our normal distribution. Mean is 0 because it's the standard normal, and it says z greater than or equal to c is 0.95. So right of some value should be 0.95. 0.95, and the only way to be right of that would be if your value c, your z value, was very far left, right? Because that will give you a total of 0.95. But we don't want a right pointing probability, we want a left pointing probability. Good news about how this is written, because this is pointing all the way right, it's very easy to say that there is now just 5% or 0.05 left of C instead. And that's the one that we'll plug in for our CAS. If you do a bunch of inverse normals, all you really need to do is rip the same syntax down and then just replace the starting value with the area. That's what the first thing is, area. Next one is the mean, next one is the standard deviation. Since we're still working with Z, we can just leave those as is. Mean of 0, standard deviation 1. What comes out is a negative value, which makes a lot of sense. Again, we want it to be negative because we're going left. That's only true of the Z stuff, by the way, because the center is 0. If it's like X stuff, left can still be a positive number. In fact, it often is, because like your mean could be 160 or something like that. Okay, that's all of those. What else? What else? Oh yeah, there's also conditional probabilities. Conditional probabilities work the same way as they have for all areas of study of probability, whether it's discrete or otherwise. You are still doing the conditional probability formula for it. It's just a matter of how you evaluate the numerator and denominator. So if we're having a look at 18b, for instance, it would be as follows. Probability of x less than 11 intersection x less than 13. So x less than 11 intersection x less than 13. And then you're dividing by the conditional itself, which is the right hand side of the pipe symbol. Probability of x less than 13. Probability x less than 13. As you get better at these, you'll be able to just look at that and know what the intersection is. I will still use a number line just to be sure. So the numbers of interest are 11 and 13. We'll pop those in. X less than 11 means that. X less than 13 means that. The intersection of which is just where they overlap, which is from here to here. So that means that the top bit just simplifies down to probability of x less than 11. It's the same thing. Probability x less than 11 divided by probability x less than 13. We just now need to find the numerator and denominator separately. Depending on if this is tech active or tech free, you would either use approximations or you would be using the CAS for each of these. Let's see, how bad would this be to do tech free? So for x less than 11, that would mean, well, let's get our normal distribution up. Normal distribution, we have a mean of 10, standard deviation of 0.5. The values of interest are 11 and 13. And since the standard deviation is 0.5, that means this one would be 2 standard deviations away, and this one's, okay, that's going to creep out of the scope. We only max out at plus minus 3 standard deviations. This is going to go further. If a interval of 1 is 2 standard deviations and an interval of 3 is going to be significantly more. so we will not be able to do this one tech-free. This will be a tech-active. So, for tech-active, since we are evaluating probabilities, we are going to be using the CDF. Both of these are pointing left, so lower bound's going to be minus infinity by default, since there's no given cap. Let's do the 11 one first, with the mean of 10, standard deviation 0.5, and then we'll do the 13 one. The 11 one was the numerator, the 13 one was the denominator. These are going to come out to be some decimal. I know it doesn't say anything about rounding, but the book can be a little bit relaxed about whether or not it tells you to round or not. And so yeah, that's how you do your conditional probability stuff. You always just do the intersection of the two things and then divide by whatever's on the right hand side, the conditional aspect. Any questions there? Cool. Okay. So we basically looked at everything. At this point we're running low on time, so I don't know if there's anything too crazy I can show. Let's see, is there anything... We already kind of discussed these ones where if you're finding like x values, whether they say c or k or whatever, it's still in the x domain here. You just want to make sure that your area is pointing left when you do your inverse normal. We discussed that at length, but most recently for like this sort of thing when you're looking for upper and lower bounds. So yeah, it just ends up being a matter of just playing with the probabilities you're given and flipping things around. What's this? Time taken to complete a task is normally distributed, mean of 55, standard deviation of 8. Find the probability. Oh yeah, now you want to give me decimal places. Great. Probability, randomly chosen person will take less than 50 seconds to complete the task. So I guess the only difference between like that kind of question and these kinds of questions is that these have no story behind them. It's just here's Z, here's X, find probability. In these ones, it shouldn't be too hard to identify what's X, what's mean, what's standard deviation. They literally tell you what mean and standard deviation are. And then because mean and standard deviation are in terms of seconds, and those are X related information, it means whatever else is written as seconds is therefore an X value. Or maybe, actually no, it'll never be a Z value, it'll always be an X, because standardized values don't have any inherent meaning. And so yeah, the stuff that would be relevant here would be mean 55, standard deviation 8, less than 50 just means you're going from minus infinity all the way up to 50. It's less than 50 seconds. Again, as a reminder, it doesn't make any sense for negative time to happen for a task, and yet we do it anyway, because we have to conform to the way normal distribution stuff is supposed to work, basically. So you'll get a bit of a weirdness there, but just remember that infinities and negative infinities are going to be valid for any given kind of question like that. These kinds of questions are kind of nice. So you're given like X related information, you're given probability related information, and because it's saying find mean and standard deviation, anytime you're trying to find a statistic, it's going to be this Z equation here. And because you're trying to find both, that's going to be setting up a simultaneous, which you can... I wouldn't necessarily recommend doing it the way they're doing it here, at least wording it the way they're wording it here, but whether you do a simultaneous or otherwise to find your mean and standard deviation, that will be how you solve two or more variables. We might look at this later in a review class for Friday, should we need to. Anyway, that's time. If you have anything you would like me to clarify further, let me know. Happy to stick around for a bit. Otherwise, thanks for coming.
Thank you.
No worries.
Have a good day.
Cheers.
Thank you.
All good.